recording. Maybe I should start doing this on Twitch or something. You know, we're doing class, and then there's the little, animation, somebody just subscribed. Or, yeah, that wouldn't get distracting at all. All right, let's get started. Lecture 12. Not only are we wrapping up our initial discussion of trusses, and by initial discussion, I'm going to say that after today and after our first exam, there are only two other times I think that I can commit that we're going to talk about trusses in here, and one is your project, and the other is influence lines. Dependent upon whether or not we have time for matrix analysis, we might talk about trusses there, but that's sort of like the cherry on top near the end of the semester. So we're actually wrapping things up. Now, I weighed whether or not I wanted you to bring Excel today, bring your laptops to do some Excel today. I do not think it's necessary for what we're doing in terms of truss deflections, but if you watched the video that I posted on Friday, which everybody did, right? Then you'll know that truss deflection computations tend to be very tabular, and Excel can help. Which, by the way, on your homework, got no problem if you want to use Excel, so no issue there. And we might talk about that on the exam, although I'm going to do some things to make your exam questions and whatnot as straightforward as possible on that. But we'll, let's walk before we run. Some other updates. All your homework is graded, other than the one that's assigned today, obviously. But I'm going to assign a homework today. It's due Wednesday, and that's it for the exam, okay? I'm not going to assign a homework Wednesday. I'm not going to assign a homework on the day of the exam. So you'll have a homework today, due Wednesday, and that's it for this week on homework. So if you're okay with that. Yeah. Okay, that's what I thought. Today what we're going to do is close out our last topic on the exam, which is to talk about truss deflections. Now, one of the things I mentioned in the video was that this is a little bit of a wild topic to explain, but an easy topic to implement. And the main sort of star of the show of the last lecture was energy. The idea that whenever you apply a load to a system, the system responds by deforming, okay? And I used the example of Link from The Legend of Zelda drawing a bow, right? You have the arrow, on the knocked on the string, you draw the bow. What you're doing is you're introducing and storing energy inside that bow, and you're doing that by deforming it, right? And they are related, right? The external work done is equal to the energy stored inside the system. So the idea is that if I can quantify the energy stored inside the system, I can set that equal to the external work done and solve for the deflection, which is what I'm interested in. And as I mentioned in the initial part of the video, deflections are incredibly, incredibly important in structural engineering. Number one, we have many designs where we simply have to design the system such that it doesn't exceed a certain deflection. In your project, you'll have that limitation as well. Like, for example, a common deflection limit for beams in buildings is L over 360. And one of the reasons that deflection limit is present is because if your roof beams exceed, or your beams that are supporting your ceiling exceed L over 360, the idea is that if you have a plastered roof, that the plaster will start cracking. It has nothing to do with whether or not the structure is going to fall down and kill somebody, but obviously we wouldn't want the plaster to crack in our roofs, right? So we have a deflection limit related to the day-to-day usage of the building, what we structural engineers call a service limit state. But the other reason why deflections are important is because you have to understand the relationship between forces and displacements in order to do indeterminate analysis. So it's a good thing to talk about. Now, like I said, what we did in the lecture that I posted is we looked at quantifying the energy. And the problem with the bow example of Link drawing the bow and how that relates to structural engineering systems, and the issue is that typically we have structural systems that have a wide assortment of loads. We may have truss with loads all over the place, and we want the deflection at a particular point. So how do we quantify the energy? How do we do that? Well, the way that we handle that is we preload, or we apply a virtual load to the structure. And one of the easiest analogies or metaphors that I can think of is, I'm sure that you all probably heard of some of those types of medical procedures where they will like inject like a marker or whatnot into your blood, so that when they do the scan, it shows the veins and shows the internal structure of your body. They don't care about looking at the marker. They don't care about looking at that dye, if you will. All that does is allow them to quantify what's going on in the system. That virtual load allows us to quantify the energy that only relates to the deflection that we're interested in. And so the way that we do that is we're kind of clever. We sum up all of our energy, and we only consider the components related to that virtual load and that real displacement. And so we get this expression here, and we say, well, if I'm solving for delta 2, and that P1 can be whatever the heck I want it to be, I'll just set it equal to 1. Hence the method of virtual work. Now, I'm going to summarize the latter part of that lecture again, because I think it's relevant to the example that we're about to do. And then we're going to do a full-blown start-to-finish truss deflection example. We're actually going to compute 2 deflections on this truss, so there's going to be a lot of truss analyses. But we're going to break out all the tricks that we have in order to make this as simple as possible. So what we're doing here is a energy-based method. It's called the method of virtual work. Of all of the methods that I could show you for deflections in this course, this is the one that I think is the most important, because this method works for any structure, for any type of deflection, period. Okay? If you open your textbook and you look at the chapters, chapter 6 is a chapter on deflections using geometric methods. And then chapter 7 is deflections using energy methods. And if you look at chapter 6, you will find no discussion of trusses. Okay? Energy methods are really the only way to go to solve truss deflections. For beams and frames, admittedly, there are other ways of going about it. There's conjugate beam method, direct integration, etc., all related to the geometry of the deflected shape. But the reason I like the method of virtual work is because it's a single method that works for any structure, any time, for any loading, period. So you can take the same process and apply it to beams, apply it to frames, and it still works, which is why I focus on it so much. So just food for thought for later. So I want to go back to this example that I discussed in the lecture online, and I'm probably going to repeat myself a little bit, but I think some of this stuff bears repeating, because if some of the topics related to energy quantification and how do you take a link draw on a bow and apply it to structural analysis, if that's a little bit of a weird idea, what I want to convince you of is that the method is actually very, very straightforward. Okay? So we've got a truss here, and I've challenged you with a particular task. We are to find the vertical deflection at B. Okay? So here's the truss. Now, whenever we're talking about deflections, okay, whenever you're talking about deformations, okay, the constitutive properties of the structure will become important. Either A, you need those properties in order to compute deflection, or B, you need to solve for those properties such that deflection doesn't, exceed a certain value and whatnot. So you're going to know, what's going on with the cross-sectional area of each of the members, and then you're going to know what's going on with the material. So here, I've told you how big around each of the members are, and I've told you that each of the members are made out of aluminum. So we'll say that the Young's modulus E is 10,000 KSI. So the first thing that we do is we solve the truss. Okay? Typically, method of joints makes a little bit more sense here because we're solving the entire truss. You got to solve the whole thing. Okay? And I'm going to denote these with big F's, capital F. Okay? Now, I did this. I just said, here's the truss, and then here's the answer, because we've actually already solved this truss before in class. This was the very first truss example that we did. So if you're wondering, where do these values just miracle themselves onto the slide, open your notebooks, go to truss example 1. This is the example that we did together in class. Okay? So here's step 1 is to solve the truss. Now step 2 is you take all the loads off the truss. Take that 10 kips, kick it away. Take that 20 kips, get rid of it. Take that 15 kips, throw it in the trash. Take all the loads off the truss. And we are instead going to do a second analysis of what I'm calling a virtual structure. Okay? Now the virtual structure, what I'm doing is I'm only placing a single load on the structure. Think of that single load as that dye packet, whatever they inject into your veins to make the medical scans easy to see. That's what that is. It's that marker for us, that tag for us. Okay? I'm placing a single load. Okay? So a couple questions. Why am I placing it at B? Well, I'm placing it at B because I want to find the deflection at B. That's you place it wherever you want to find the deflection. Why is it vertical? Because I want to find vertical deflection. If I wanted to find horizontal deflection at E, I'd place a horizontal load at E. Okay? Now, why is it going downward? Okay? Why don't I place it upwards? The reason why it's going downward is because I'm taking a look at the original structure, and I'm looking at the original loads, and I'm thinking, B probably deflects downwards. So I'm taking that load and I place it downwards. If my assumption is incorrect, that will be revealed in the math. It will be very easy to see that my assumption is incorrect, and we'll just find that, oh, I assumed downward, I got a negative answer. It's going upward. So it's really easy to handle. Now, what you have to do, you have to solve the truss again. Okay? So one of the things that does kind of suck about deflection-based analyses is that you tend to have to do multiple analyses. So if you're doing a truss analysis and you want to solve for deflection at a given joint, you have to solve for the real forces, and then you have to solve the structure again for the virtual forces. Now, usually what happens when you're solving the virtual structure, you've got this big old truss and there's only one load on it. Okay? So there's a lot of tricks that you can use, hopefully, to make your life a little easier. If you have a truss and it only has one load on it, there's a chance there might be some zero force members on that truss. And if you can identify those zero force members quickly, you can make that truss analysis go a heck of a lot faster. The other thing you can do is look at this truss. Take a look at this truss and what property screams at you looking at this truss. It's symmetric, right? So I only need to solve half the truss, and now I've got the rest of it solved. So between exploiting symmetry, between recognizing zero force members, hopefully you can make that virtual analysis a heck of a lot easier for yourself. Okay? Now, one of the things to note on the unit side of things is that when you apply this unit load, you can think of it as like 1 kip or 1 kilonewton. Technically, it's unitless. So before, when we had internal forces of 15.6 kips and 3.1 kips, these internal forces are unitless. So it's for example, member DE has 0.75 in it. You can think of it as 0.75 kips, but it's technically unitless. And the other thing to note, in your virtual analysis, the load is pretty small. So these internal forces are going to be a little bit smaller, so that's okay. If you have a regular truss analysis, you're thinking, oh, that member's got 50 kips in tension or 70 kips in compression. Here, the answer is like 0.6. That's okay. Smaller loads, smaller forces. Everybody okay? All right. So in terms of the method of virtual work, what you've now got are 2 sets of data for the truss. For every member in the truss, you've got the real forces, which I'm calling capital Fs, and the little forces, little f's, are the virtual forces. So big F is in kips, little f is unitless, and in terms of the remaining properties of the members, I've got E, which is the Young's modulus of each member, in KSI. So I could have all sorts of different members. I could have this member be wood, this member be steel, this member be aluminum. We typically don't do that in civil engineering, but we could. Each member has a cross-sectional area, so E's in KSI, A is in square inches, and I'm ultimately going to be doing this. So the member length, what units should I use for the member length? If this is in kips, this is in KSI, this is in square inches, so that the units are all copacetic, what should I be expressing the member lengths in? Inches, right? So whenever you tabulate your data for the truss, make sure that you're tabulating your member lengths in inches, okay? So that everything's consistent from a units perspective. When we do beams and frames, we're not going, there's two ways of going about it, let me say. You can convert all of your lengths to inches and then do your math, or you can apply a conversion factor. And it's usually a lot easier to apply the conversion factor, but the point is you have to apply it. So if you want to think about this, the conversion factor would be 12, because I'm converting the lengths to inches, right? And I'm doing that by multiplying all the lengths by 12. Okay, so here's my table that I've set up, and I'm doing little f, big F, L, E, A, because this is ultimately what I want to compute for each member. And now all I got to do now is fill in these values. So what am I doing? I'm taking my truss analyses and I'm putting, okay, member AB. This is what I got for the virtual analysis. This is what I got for the real analysis. This is what I got for the virtual analysis. This is what I got for the real analysis, et cetera, et cetera. In terms of sign convention, because I got to put a sign somewhere with these, I got to call the ball somewhere. What I'm going to do is I'm going to say that I'll record tensile forces as positive. I don't care if you record compression forces as positive. It doesn't matter. You just have to be consistent. If you're using tension positive here, you got to use tension positive here. If you're using compression positive here, you got to use compression positive there. Because ultimately, so like take member AB. If this is in tension and this is in tension, bless you, because both of the members are experiencing the same type of load, they're both in tension, when you compute this, it will come out positive. And that's why you have to be consistent with your sign convention. So now for every member, I've got a little f, a big F, an L, an E, an A. And so now I just compute this. So little f times big F times L divided by E divided by A gives me that. Bam, 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 divided by that, bam. Bam, 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 divided by, so on and so forth. So you're starting to see why Excel would be pretty useful here, because you're just doing the same thing over and over again. That's something computers love to do. And so what you're doing is you're just chugging that out for each row, summing it, because this sum is the energy expression related to that deflection. And so when I sum that up, I get a sum of 0.237. Notice how each of these terms come out positive. What that means is that my assumption was correct. Okay? If I assume a positive value, if I assume a downward deflection and I get a positive value at the end of the day, what that means is I assumed correctly. So go back to the problem statement at the beginning. My goal was to determine the vertical deflection at B. We analyzed the original structure. We then took all those loads off and analyzed the virtual structure, and we put a downward unit load at B. We got a positive value, which means that assumption was valid. The deflection at B in the vertical direction is 0.237 inches downward, and that's the answer. I'm going to stop for a sec and see if this makes sense, if anybody has any questions.
Are you going to show how to solve for little f?
Yeah, we're doing that here in a bit, yeah. Don't worry. In fact, we're going to do little f twice. Even better, yeah. Any questions? All right, this is our example that we're going to do for the rest of class today. It's a small truss, which, by the way, I'm going to go ahead and answer an exam question because I know I'll get asked this question. So, Dr. Mike, are you going to give us some ginormous truss deflection problem so we have to solve this ginormous truss 3 times on the exam? Yes, because I'm mean. No, I'm not doing that. I'm not that mean. I mean, you are going to have a problem assessing truss deflections, but it's not going to be this, ridiculously huge truss, because once you've demonstrated that you can solve a truss, what am I going to do? Make you just do it over and over and over again? At some point, it's like it's time to move on. Okay, so we're going to determine the vertical deflection at joint C, and then we're going to determine the horizontal deflection at joint B, okay? So what this means is we're going to have 3 separate truss analyses we got to do, but we had a tiny truss, so it's not that big of a deal. I've got the truss labeled here, and notice I've got all the cross-sectional areas labeled. For all the members, I've told you that E is 29,000 KSI. Anybody know what material I'm referring to if E is 29,000 KSI? What's that? That's steel, yes. You know how like the unit weight of water is 62.4 pounds per cubic foot, and that's just like a number that you should have burned into the back of your head by the time you graduate with a civil engineering degree. So E is 29,000 KSI. That's another number. Especially if you have me for steel design, I will burn that number into the back of your head by the time you're done with me. So you're just going to remember that. Okay, let me pull up the notebook here because I've got this also copied on the notebook, so there's nothing here that isn't there. Okay. All right. So I'll give you all a sec to copy this down, and then we'll get rocking and rolling. And we're going to try and do these truss analyses as quick as possible because I don't want to be slowed down by that. I mean, we're going to have to do these truss analyses repeatedly, but hopefully you'll start to see there's some tricks that we can use to make this go quick. Okay. So I'm going to give you a sec to copy this down, and then we're going to break out every rabbit in the hat that we can. So I'll give you a sec. If we were Twitch streaming, this is where I'd go through all the bits and all right, everybody good? Okay, I also copied the truss down here again because I'm kind of lazy. First thing that we're going to do, let me get this out of the way. First thing that we're going to do is the real analysis. And by the real analysis, I mean the big F values. Okay? Now, in order to do this analysis, we have to solve the truss. If we're going to solve this truss, what do you think we ought to start doing? Start with doing? Support reactions. There you go. We got a roller here, and we got a hinge here. The hinge has a vertical reaction and a horizontal reaction. There's only one vertical reaction here. Does anybody know what this vertical reaction is going to be? 80. We got 80 down, we got to have 80 up. So this is dy is 80 kips. Now, the thing with these two here is that there are reactions in the horizontal direction, and there's two of them. There's a horizontal reaction here and a horizontal reaction here. So what I'm going to do, I'm going to be formal about it. I'm going to sum moments at A. Or sorry, no, sum moments at D. I meant sum moments at D. So if I sum moments at D, do I have to consider dy? Do I have to consider the 60 kips? Do I have to consider the 80 kips? You bet. 80 kips times what moment arm? Yeah, I see how you said that because it's the 2 inches, but the distance is 6 feet. That I can see why you did that. 80 times 6 going this way, right? And what must that be resisted by? There's a horizontal reaction here times a moment arm of 8 feet, right? So if I was a betting man, I would say the AX probably goes like that. Is that a fair statement? So 80 times 6 is 480. So that's going to be 60 kips. And if this is 60 kips, what's the horizontal reaction right there? Oh, hold on. 120. Because I got 60, 60, because they're both going in the same direction. That's 120, right? Do y'all see that? So that means that this goes like that. Now I'm going to stop for a sec. Did I do that too fast? If I did, or if there's something you're like, wait, what the heck did you just do? You just miracled some stuff onto the screen. Let me know, okay? Hopefully we've been doing these kind of fast that, or we've been doing so many of these that doing them kind of fast should be okay. Okay, so far so good? All right, okay, so help me out with something. We need to solve the entire truss, right? So we need to use method of joints or method of sections? Probably joints, right? So what I'm going to do, this is what I'm going to do. I'm going to blow up this entire truss and just try and do the method of joints analysis all at once. So let me scroll down a little bit. Let me see if I can do that right here. Now, by the way, does anybody know what the slope ratio of that diagonal is before I do this? 3 to 4, right? That's 4, and that's 3. Okay. So I got that, 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 and that. Let's put our forces on here. That's 80, 60, 120, 80, 60. We'll sort of like highlight our members. And we got a member like that. What joint do you think we ought to start with? So this is A, B, C, D. What's an easy joint to start with? What's that? B?
D.
D. Well, we could start with D, but D has 3 members in it. Let's start with either A or C. They only have 2 members. I'm lazy. All right, let's start with A. Let's start with this joint down here. So we got a member like this and a member like that. So sum of forces in the x direction tells me what? If this is 60 kips to the right, what's this? 60 kips to the left. And if that's 60 kips to the left, okay, well, what's going on with sum of forces in the y direction? What's this? It's 0. There's nothing going up or down, right? That's a 0 force member. So we'll just do that, I don't know, do like that. Just say that's a 0 force member. Do y'all see what I did here? Is that okay? Did I do that too fast? Is that good? Okay. Now, before I move on to the next joint, what I'm going to do is this, I'm going to say, okay, if that's 60, that makes this 60 like that, and that makes this a 0 force member as well. See what I did? I said if that's 60 going to the left and that's 60 going to the right here, and if it's 0 there, it's 0 there. Now again, I'm lazy. What's an easy joint to solve right now?
C.
C. Let's look at joint C. That's joint C. So somebody tell me what's going on with that vertical member. 0 force member. What's going on with this force? 60 kips to the left. See, this isn't so bad, right? When you blow the truss up, you can kind of do this kind of quickly. So this is 0 force member. 60 kips. And then before I move on to the next joint, let's transfer that out. With me so far? Now, in terms of this diagonal, does it really matter which one I do? I could do joint B or do joint D. Which one do you want me to do?
B.
B. All right, let's do joint B. There's one load here, two loads there. It just seems easier. So let's do joint B. All right. And what makes joint B easy is that the slope ratio is already respected. Watch this. What do I got going on here? 60 to the right. I need 60 to the left, right? 80 down, 80 up. So that makes this 60, makes that 80. What's the ratio of 60 to 80? 3 to 4, right? Already respected. And then if I transfer these up here, just for formality's sake, so 60, 80. Let's look at this joint D here at the top, just for formality's sake. What do I got going on here at joint D? I got 120 to the left, 60, 60, 120 to the right. 80 up, 80 down. Boom. We're done, right? There's your real analysis. So what we'll do is, just to summarize this, and I know it's not to scale, but that's okay. So, wait, that's 80, sorry. Okay, so now let's just record our internal member forces. So what's going on with these two vertical members? 0, right? This is a 0 force member, 0 force member. All right? Help me out with this one. What's the magnitude of the force inside this? Is it 60? Is it tension or compression? Tension. 60 in tension. What about this one? 60 in tension, 60 in compression, and this one? Say it again. There we go. So 60 tension, 60 in compression, 100 in tension. I'm going to give everybody a sec, and we'll stop. Give everybody a sec to catch up. Yes, sir?
So why are the vertical members 0?
Why are they 0? Just because of the loads that we have applied. That if I yank here and yank here, there's just no vertical load. If I had a vertical load on this joint, this would not be a 0 force member. If I had a vertical load on this joint, it wouldn't be a 0 force member. There just isn't that load present there. And if I'm being honest, part of this problem was designed to get some 0 force members. Because here's the thing, even if on the real analysis you don't have many 0 force members, you probably will in the virtual analysis, because remember, we're kicking a lot of those loads off. Yes, sir?
How do you get the 100?
60 squared plus 80 squared, square root. All right, everybody with me so far? Okay, now, let's do the vertical deflection. What was the task for this problem? Vertical deflection at what? What did it say? Let me scroll up. We're determining the vertical deflection at joint C, okay? So now we're going to do this truss analysis all over again. And I'm going to need your help on some bookkeeping here later on. Virtual analysis for vertical deflection at C. And these are going to be little f values. We're going to do another truss analysis here in a bit and get some more little f values. We'll take it one step at a time. So what we're now going to do is we're going to do a brand new truss analysis. Start from scratch. Wait, hold on. A whole nother one. All right, and we had a diagonal member about like that. Yep. And that's at a 3 to 4. Now, this is for the vertical deflection. Here, hold on, wait, let me do this. Before we start the analysis, let's be diligent. Okay. This dimension is 6 feet. And this dimension is 8 feet. Now, I need to name these. A, B, C, D. Let me put that somewhere else. Let's do that there. A, B, C, D. Bam. So we're going to do a brand new truss analysis. And this time we're going to be looking at the vertical deflection at C. So this is joint C. Okay. I'm going to take joint C and I'm going to apply a vertical load of 1.0. Now the question is this a downward load or is it an upward load? Okay, you're saying downward. Why are you saying downward?
The load of B would want to pull that down.
Okay, so what you're doing is you're going back to this analysis and you're saying, I think that's probably going to go down. So what you're saying is load that down. Okay, let's do that. If we do this, and at the end of the day, when it's all said and done, we get a negative answer, that does not mean we need to develop significant emotional distress. All that means is that our assumption was incorrect and it in fact deflects upwards. And to be clear, while I think it's pretty easy to see that this is going to go downward, there are some instances where that's not so easy, okay? When you got overhanging beams and all sorts of weird stuff. And so you have to just be diligent, go through the process, track your signs, and let the math work out the way it works out. So for here, it's simple. Later on, maybe not so much. Okay, so we do the truss analysis again, start to finish. We got a roller here, a hinge here, which means we have a vertical reaction at this hinge. What's the vertical reaction at the hinge?
1 up.
1 up. And just like before, what I will do is sum moments at D to figure out what that reaction at A needs to be. So we'll sum moments at D. So sum moments at D, I get 1 times 6 has got to be matched by AX times 8 feet, right? That's the same thing we just did, right? So AX is probably got to go like that. So what's AX? 3/4. It's not 3/4 kips or 3/4 kilonewtons or 3/4 pounds. It's just 3/4. Okay? So 3/4, which is 3/4 that way. And so AX is 3/4. And if that's AX, what's DX? There you go. Now, to be crystal clear, I'm skipping a lot of the formalities that would make certain faculty in love with system parameters cry. I'm an engineer. But here's the thing, if you need to go through that, go through it. You're not going to hurt my feelings. Do what you got to do to solve the problem. Just do it correctly. So I'm just doing it kind of quick because I recognize it. All right? Bear with me so far? Okay. So we're going to do the same thing we did before. Take this, do a big old method of joints analysis. So now I'm going to do that blow up again. All right, hold on. There we go. Let's do that blow up again. So put our loads put our little sort of like shadow truss. So you can kind of see what I'm doing there. Okay. And then, let's see, D, C, A, B. While it is a completely different truss analysis, it's still the same truss. So maybe we can use the same conclusions and the same strategy before this time. Where do you think we should start?
Can we identify zero force members? Will it be the same as the last one?
So yes and no. Should we try and identify zero force members? Yes. Are we going to get the same zero force members as we did last time? Not necessarily. Okay. Which joints did we do first? We did A and C first. Let's do A and C first again. So let's start off with A. So let's look at joint A. So 3/4 to the right tells me what's going on right here. And what's that going on right here? 0. Simple. And then we'll transfer those to the members on the opposite side. All right, then which joint did we do? We did joint C. Let's do joint C. So now tell me what's going on with joint C, huh? What's going on with this vertical member? 1 up. Interesting. Did we get that was a zero force member last time? So last time it was a zero force member, now it's not. It's because it's different loads, right? That can happen, right? Different load situation, different conclusions, all right? Now what about that horizontal? 0. So 0. And then transfer that down. 1.0. Which joint should we analyze now? Maybe B? Isn't that what we did? We did A and C, then we did B, and then we looked at D at the very end. So let's see what we got going on here. We'll scroll down a bit so I'm not squunched here. So 3/4 to the right means I got 3/4 to the left, 1 down, means I got 1 up. Does that respect the 3-to-4 slope ratio? Yeah, right? And then as a final check, if I transfer these forces up here, don't look at the equilibrium, just transfer the forces. So 3/4 to this direction, and 1 up, 1 down. Does that respect equilibrium at joint D? You bet, right? 1 down, 1 up. 3/4, 3/4. Boom. So now, in order to transfer these forces, all right, so this is down. It's about, wait, what'd you say?
Make that 3/4 A. Looks like a 3 here.
It's a 3. My handwriting's horrible, you know, but thanks for pointing it out. Thanks for pointing out my horrible handwriting.
Well, mine's just bad.
I'm just messing with you. I'm just messing with you. Okay, all right. So let's see what we got. That's a 0 force member. This is a 0 force member. Now what about this vertical BC? It's 1. Is it tension or compression? Compression. So this is 1 compression. This AB. 3/4 compression. And now the diagonal. What's the diagonal going to be? 5/4, right? 1.25, and that's in tension, right? With me so far? Just square root of the sum of the squares. So 3/4 and 1. That's 1.25 tension. So far, so good? And before we stop and go to Excel, I'm just going to scroll up here real quick and write A, B, C, D, just so we have it referenced later. Okay, does everybody have this written down? Now, what's the formula that we're going to use? Little f times big F times L all over what? EA, right? So, now how many members are in this truss? 5? Okay. Everybody got this? Okay, let's break out some Excel. Because I'm lazy here. Okay, so, oh, that's the wrong keyboard. Okay, so little f, big F, and this is in kips. L, what units for L? E, A. Okay, let me get this a little bit out of the way. There we go. Now, what are the members? Let's be alphabetical. So maybe AB, AD, BC, BD, CD. I get them all? Okay. Now, before we start filling these in, let's look at the other properties. What was E? 29,000. So oh, that's a lot of truss members. Okay. All right, what about the areas? 2, 2, 2, 2, and then this one's 1.5. That's BD. So 2, 2, 2, 2, but then that one's 1.5. This one is 1.5. Did I get that right? Okay. Now let's take member AB. What do I put in this cell right here for AB? How long is member AB? 6 feet or 72 inches. So 6 times 12. What about member AD? There you go. BC is 8 times 12. BD, what's that one? Yeah, 10 times 12. And then CD is 6 times 12. There you go. Okay, so we filled in this data right here. Now we've got the little f's and the big F's. We did the big F's first, so let's do the big F's. Now, help me out here. Let's start off with member AB. What was member AB experiencing? 60 and what? So what do I put right here? Boom, negative 60. So this goes, oh wow, we're running short on time. Let's do this quickly. All right, negative 60. What about AD? 0. BC? 0. BD? And CD? Say it again. Okay, positive 60. All right. Okay, we'll do this part quick. AB. All right. AD. BC. BD, 1.25. And CD, 0. So, and I'll probably post this table. I'll put the table in the notes. But all you do now is just little f times big F times L divided by E times A. I just copy that down. And so what's your deflection? Boom. So, what did we get? We got a positive value, which means our initial assumption was correct. The deflection at C, going down, is 0.401 inches. Since we ran short of time, I'll do the horizontal deflection as a side video, because that one's real easy, okay? Man, we're rocking and rolling. All right, sound good? Hey, before I leave, Wednesday, exam review. Come prepared, ready to ask questions, okay? We'll talk about exam format, but come prepared with your questions. That's all I got.